Okay, so what we're going to do is set up a problem that is pretty comprehensive. The objective is to construct our own titration curve using computations at various points. So let's just start with a fairly simple example. Let's say that we want to take a 0.1 molar solution of acetic acid, and we're going to start with an initial volume of 20 milliliters of this acid. And we're going to titrate this with a 0.1 molar solution of NaOH. So in order for this titration curve to take shape, because I want us to graph this by hand, and then I want us to turn around and graph this with Excel. And so in order for us to have enough points, I want us to do increments of 1 milliliter. So let's start with 0. And we are going to go in integer increments. Once we get to 9, then I want us to do 9.5. I want us to do 9.6, 9.7, 9.8, 9.9, 9.95, 9.97, 9.99, 10, then again 11, increase by integers until we are at 20, and then I want us to go 21 through 25 milliliters. So there are a lot of data points to calculate for this. I think a lot of them are going to end up being fairly redundant. But in order to really understand how constructing this titration curve works, in order to really understand and master all the mathematical principles associated with this, I believe this exercise becomes really critically important, so that no matter what question I ask you on your take-home exam or on a problem set or in class or in lab, that you'll be able to handle it. And so what I'm going to do is do the first few. We're going to group them into different types. For example, the 0 calculation really stands alone. All of the computations from 19 to just before that equivalence point and including anything up until that point except 0 are really very much the same computation. The equivalence point, of course, we know from experience in class that this one stands alone. And then, of course, anything above the equivalence point will stand alone. So really, we're going to look at just 4 different calculation types. So let's get right to it. And first of all, consider when all we have is the initial concentration of our acid and we've added no base to the solution. So the relevant equation is going to be acetic acid. Of course, we know that this is aqueous, plus water course, since this is a weak acid, we know that this is at equilibrium. We also know that the Ka for acetic acid is 1.8 times 10 to the minus 5. And my chemical products are the hydronium ion, which of course is also aqueous, as well as the acetate anion, which is also aqueous. The methodology that we will use to find this initial pH is going to be determined through our familiar friend, the ICE methodology. So the initial conditions, we know that we have a 0.1 molar solution of our undissociated acid. We know that some unknown molarity will dissociate to produce the same unknown molarity of hydronium and the same unknown molarity of acetate by virtue of our balanced chemical equation. And at equilibrium, we have 0.1 minus x. Now, we've talked many times in class about when the initial concentration of a reactant is much, much greater than K, and by much, much greater we mean by a factor of 1,000 or greater, then that x becomes so insignificant that we can ignore it. So 0.1 minus x becomes equal to 0.1. And of course, each of these will be x. And by virtue of our equilibrium expression, Ka, which is equal to 1.8 times 10 to the minus 5, is equal to x squared over 0.1. We've solved this explicit mathematical equation numerous times before. Cross multiply, take the square root of both sides. You'll find that x is equal to 1.35 times 10 to the minus 3. This is equal to the concentration of hydronium. I know that if I take the negative log of the concentration of hydronium, which we know is 1.35 times 10 to the minus 3, I will have the pH. And in this case, the pH should be right around 2.88. So this should be the initial pH that we read from our probeware before we actually begin our titration experiment. So what I'm going to do now is I'm going to open up an Excel spreadsheet. And we're going to have volume added. Volume added is our base, NaOH. And we're going to have our pH. And so when I've added 0, the initial pH should be 2.88. I'm going to go to 2 units past the decimal point. And so, actually before I close this window, this is something we have done a lot in class. I really do not expect this to be a problem at this point. So in going back, we have now computed the first type. So this one is now completed. Now, when we add 1 milliliter of base, we have a new equilibrium, a new type of chemical reaction. We have acetic acid, but rather than it's simply dissociated in water, now it's going to react with the appropriate equivalents of hydroxide that we've added at a given point. This is still going to be governed by an equilibrium constant, but the equilibrium constant is no longer Ka. We will produce acetate ion, in fact more specifically sodium acetate, the conjugate salt of acetic acid, and water. With this particular equilibrium is best represented with the Henderson-Hasselbalch equation. And the Henderson-Hasselbalch equation yields that pH is equal to the pKa of the parent acid plus the log of acetate in terms of its concentration, or how many moles there are, that also works, divided by the concentration of the undissociated acetic acid. We have 20 milliliters of 0.1 millimole per milliliter. Meaning we have 2.0 millimoles of acid. We are going to add 1 milliliter of 0.1 millimole per milliliter. What this means is that I will neutralize 0.1 millimoles of my acid. Of course, by doing this, I will also consume all of my base, and I will produce 0.1 millimole of acetate anion. Now, the pKa is going to be a constant at a given temperature. We derive this constant from the negative log of the Ka. For acetic acid, its known value is 4.74. And we're going to add to that the base 10 logarithm of 0.1 divided by 2. And this will equal the pH of the particular system when I have added 0.1 millimole of base to 2 millimoles of acid. So now what you'll want to do is use your calculator and simply plug and chug. And when we do this, we find that the pH at this point is 3.44. Again, rounding this to 2 places after the decimal. Now, remember when we have collected an experimental titration curve in the lab, that we initially see this bump. And we also see it here. By simply adding 1 milliliter of base, we've increased our initial pH by nearly 0.6 pH units, which is actually pretty large considering we've only added 1 milliliter. Of course, now we want to go to our spreadsheet. And when we've added 1 milliliter, it is 3.44. Now, in order to save time, I think that you can certainly go through these methodically and do the calculation new every single time. But I think what would be even more valuable get the right program open here, that would work. Here we go. If we write our reaction, acetic acid plus OH minus yields H2O plus acetate anion. For each successive 0.1 millimoles that we add, and that's what we're doing every time we do a new point on the titration curve. Remember, Henderson-Hasselbalch says that pH is going to equal pKa, which we now know is 4.74, plus the log. So after 2 milliliters, I've added 0.1 and another 0.1, and now I have 1.8. And after so that's for 2 milliliters. After 3 milliliters, it's 4.74 plus the log of 0.3 over 1.7, and then 0.4 over 1.6, and then 0.5 over 1.5. Once this makes sense, my advice is not to do a new equilibrium expression every single time. It simply takes too much time. And then we can go ahead and calculate these values, and I'm going to do this real quick. Then I'm going to pause the screencast and simply fill in all of those values up until 9 milliliters, just to save us time so this podcast doesn't go on forever. So again, 4.74 plus the log of 0.2 divided by 1.8. That gives us 3.78. And then for the next one, 3.99. I actually have discovered a small mistake I made earlier. For the first point, I did 0.1 over 2, and it should have been 0.1 over 1.9. So let me redo that one as well. So for the 1 mil, it's 4.74 plus the log of 0.1 over 1.9 instead of 2. Hopefully by now you can see why you cannot use Henderson-Hasselbalch for the first point, because it would be 0 over 2. The log of 0 is undefined. You cannot set 10 to any exponent and have it equal 0. So mathematically, it's intractable to do it that way. So 4.74 plus the log of 0.1 over 1.9 is actually 3.46. It doesn't make a huge difference, but wrong is wrong and right is right. So it should be 3.46. Notice the difference between these two values is about 0.32. Initially we had 2.88. That difference is about 0.56. This difference is about 0.21. So now we're getting into the buffering region where, even though we're adding the same amount of base each time, the increase in pH is becoming more and more diminished. And for the 4 milliliters, it's 4.74 plus the log of 0.4 divided by 1.6. That is 4.14. Notice that changes by 0.15. And then when we do the log of 0.5 divided by 1.5, 4.26, a change of 0.12. So an initial bump on the titration curve and then it begins to smooth out like this. And that's really what we've seen when we do a titration in the laboratory. So I'm going to take a time to post all of these. I'm going to pause the screencast just for a couple of minutes, and I'm also going to do points for 6, 7, 8, and 9 milliliters and then show you that data. So I have entered the pHs for various volumes, and I have gone to just before the actual equivalence point, and the pHs are rendered in column B, while the volumes of the NaOH added are in column A. Once we get to 20, we should have exact and complete neutralization. So let's talk about how we handle probably the most difficult point on the titration curve. So once we've achieved exact and total neutralization, all of our acetic acid and all of our hydroxide have completely reacted one with another. And so the only molecule of significance in the system at this point is our conjugate salt. There is 0 acetic acid, there is 0 NaOH, there is 2 millimoles in a volume of 40 milliliters, giving us a concentration of acetate of 0.05 molar. So it is the hydrolysis of this salt that now controls the pH of our system. So sodium acetate plus H2O will yield the strong base NaOH, which we know will completely dissociate. And the weak acid, acetic acid, which will not significantly contribute to the pH of the system. This now is no longer Ka, but rather Kb. And we know that Ka times Kb is equal to Kw, which at room temperature is experimentally measured to be 10 to the minus 14. We know that this is 0.05 molar. Once we solve our system for X with our ice diagram, 0.05, again, this is still much larger than 5.6 times 10 to the minus 10. And I get that value by dividing 10 to the minus 14 by the Ka of acetic acid. So when I go to a new page to show you the math, we have 0.05 divided into x squared equals 10, excuse me, not 10, 5.6 times 10 to the minus 10. X squared is going to be equal to 1.12 times 10 to the minus 12. Now, if we're interested in just approximating, that's about 10 to the minus 6, which would equal the POH. Excuse me, when I take the negative log of 10 to the minus 6, that would equal the POH. Getting a little ahead of myself here. The negative log of X is the negative log of hydroxide, which is 6, which is the POH. Therefore, the pH should be around 8. But to get a more precise value, I'm actually going to prostitute myself and actually go to my calculator, which I pretty much hate. So first of all, 10 to the minus 14 divided by 1.8 times 10 to the minus 5 gives us a value of 5.555 repeating times 10 to the minus 10 times 0.05. Take the square root, and I get 5.27 times 10 to the minus 6. I'm going to take the negative log of that value, and I get 5.28. When I subtract from 14, I get 8.72, and that's a much more precise answer. So the pH, when we actually plug in all the values, is 8.72. That's my equivalence points pH. I think that's consistent with the notion that we are titrating a weak acid with a strong base. The equivalence point pH should be alkaline, and according to our calculations, it is alkaline. And notice what happens. I have added 0.01 milliliters of base. That is the equivalent of 1/5 of a drop of base. And the pH changes by 0.68 pH units. Yeah, that is definitely the equivalence point. Okay, so going back to what we have done thus far in this huge problem, we have covered our initial pH, all of our pHs up into the equivalence point, and now we've covered the equivalence point. The last examples are all of the same type. When I over titrate by adding more base. Here we should see a significant amount of base produced, and therefore a very high pH. So we're going to elevate from the 8.72 to the 11, 12, 13 range fairly quickly. So all of these are going to be of the same type. So let's just do 20.01 first. And then we'll do that value together. And then any other value, you're just doing the math a little bit differently. So I'll pause the screencast one more time, and then I'll bring it back up, and we'll plot all these points and see just how much all of this work mimics a titration curve that we would produce in the laboratory. So of course, we're going to use the same equilibrium we use for Henderson-Hasselbalch. There's just one very important difference. So we have acetic acid, and we know initially we had 2 millimoles. We are adding hydroxide. Now we are adding 20.01 milliliters, which means we are adding 2.001 millimoles of base. All of the acetic acid is now neutralized. What I have left over is 0.001 millimoles of base in a volume of 40.01 milliliters. Now that's going to give me a concentration of OH. And that concentration is 2.4994 times 10 to the minus 5 molar of OH minus. If I take the negative log of this number, I will obtain the POH, which is 4.60, which now means my pH is 9.40. So by adding a very small amount, and I'm going to change this from 20 to 20.01, this now is 9.40. And I'm just going to call it 9.38, which is a little bit more. I'm rounding a little bit less to get a more precise answer. Okay, so so the rest of these is the same kind of math, only now I'll have more and more OH left over after equilibrium. And so I guess I could do a couple more of these with you guys. So let's do the 0.1, the 0.2, the 0.3, and the 0.5. I'm going to actually get a new sheet. So if I add 20.1, 20.2, 20.3, 20.5, and 21, I'll have an excess. Now these are volumes that I'm adding. In terms of millimoles, I'm adding 2.01, 2.02, 2.03, 2.05, and 2.1. In each case, I have to neutralize 2 millimoles of acid. Which means I have 0.01 divided by 40.1. I have 0.02 divided by 40.2. I have 0.03 divided by 40.3. 0.05 divided by 40.5. I have 0.1 divided by 41. Now my concentration of OH minus and my POH, and then of course the pH of the solution. So taking these one at a time, 0.01 divided by 40.1 is 2.494 times 10 to the minus 4. The POH is 3.603, which means the pH would be 10.397. Okay, now with the second point. 0.02 divided by 40.2 . 4.975 times 10 to the minus 4. POH is 3.303. pH is 10.697. 0.03 divided by 40.3. 7.444 times 10 to the minus 4. POH is 3.128. So our pH is 10.872. 0.05 divided by 40.5. 0.00123. POH is 2.908. pH is 11.092. And finally, 0.1 divided by 41. 0.00244. POH 2.613 with a pH of 11.387. All right, I know that was boring. Notice the trend though, as I add just a little bit more base each time, the pH increases from 10.4 to 11.4 by adding a total volume of 0.1 milliliters. That's pretty significant. So now we can go to our spreadsheet and write these values down. We've got 10.397 and 10.697 and 10.872, 11.092 and 11.387. Before the advent of probeware, my preference in collecting this data using the burette was to actually draw your curve using the spreadsheet. I think the days of hand graphing have died a horrible death. They should have died a horrible death. We're no longer kindergarten boys and girls. But some people hold on to what they consider to be the good old days. But I think if you're honest with yourself, you just see the superiority of using the data collection software. So now all we have left are 22, 23, 24, and 25. So let's quickly go back to those. So let's see, we have 22 mils, 23, 24, and 25. So that means we have an excess of 0.2 of base and a volume of 42, 0.3 of base and a volume of 43, 0.4 of base and a volume of 44, and 0.5 of base in a volume of 45. So the next thing we want to do is calculate the concentration of hydroxide. Point 0.00476 molar. That's a pOH of 2.322, which will be a pH of 11.678. 0.3 divided by 43, 0.00698 molar. pOH of 2.156, pH of 11.844. Point 00909 molar. pOH of 2.041, pH of 11.959. And finally, point 0.01111 molar. pOH of 1.954 and a pH of 12.046. And so now we're going to plot these last few points and then take a look at our theoretical titration curve. This should make you appreciate the probe wear even more, because just doing this theoretically is a mountain of work. The instrument does all of this for us within the space of 5 minutes. And not just all the calculations, but the computations as well. All right, so volume added, pH, let's select. And we want to insert a chart. We'll go scatter. And that is a pretty damned nice titration curve. Now, one thing I want y'all to notice, all the work we put into this and then how easily the probeware computes this for us. So this is a textbook weak acid, strong base titration curve. The equivalence point gives us an alkaline pH. Half equivalence point gives us our pKa. And I mean, this is just really, really nice. So this concludes the nature of this podcast, which is just to show you how to go through every single different type of computation, whether it's you doing the initial pH using ICE methodology, from the time I add a single drop of base until just before the equivalence point where I use Henderson-Hasselbalch, to the equivalence point in which I use the hydrolysis of my salt, to when I over titrate, in which I just compute the concentration of hydroxide, convert that to a POH, and then convert that to a pH. So we can discuss this a little bit more in class tomorrow, but this should really give you an excellent primer on how we perform this very complicated type of problem.